So our main goal for today, and when we finish this up, we're going to use principles of probability to develop theorems for finding probabilities of unions or complementary events.
Where's the wing that we can use? I think it was earlier.
In the situations above, about summing dice and about looking at data in a classroom, some outcomes overlap and some do not. So let's take a gander here. These guys sum to 7, these sum to 11, which mean there's never a time when both of them occur at the same time, okay? So, just so that you have a perspective, this section right here is called the intersection. It's the intersection of the two events occurring. Now, of course, in the female and junior situation, we have some intersection. Over here, we have no intersection. So the intersection we call the null set. And we usually write it with a 0 slash through it. Again, this does not mean the number 0 is the thing that overlaps. It's saying that it's an empty set. There's nothing in it. All right. So this over here, if we were talking about just counting things that happen, this would be the number of things that sum to 7. This here would be the number of things that sum to 11. And since there is no intersection, we can write that in symbols. And the symbols pretty much go like this. If this is set A, this is set B, just to save space. We'll just call it A and B. That we have A with a U, B, and this means union, that is, or. So if I say, what is the probability of this or this happening, we just count how many times those can happen and divide it by the total sample space. So that becomes the probability. So that's called a union. Now, the other component, this here, again, if I call this A and this B here, the intersection is called A with an upside down U, so it kind of looks like an N for intersection, which that's not really what it means, but that's how I remember it. So that says A intersection B. So that is talking about this region in here. In other words, how many juniors are females, or how many females in the class are juniors. So that would be the 4 ladies that are in there. So in this case, we have 4 intersected. And if we see how many females total we have a total of 9 females. So that means 5 of them are non-junior in this class. And what about juniors? So when we count all the juniors, which we had a total of 9 also, we're going to count over here that we have clearly a bunch of male who are juniors. These are female who are juniors. These are females, and these are 5 females who are not juniors. When this occurs up here, where there is no overlap, we call this mutually exclusive. Mutually exclusive. There is no connection between the two because the intersection is a null set. Down here, it can be called non-mutually exclusive, which means there is some sort of overlap. Let's count it up. In a standard deck of cards, so let's just refresh what's in a standard deck of cards. There are 52 cards, right? There are 4 suits. There are 2 colors. You also have face cards, right? 12 face cards. We also have 4 aces, which is not a number. And then the rest are numbered cards, okay? Now, these up here are not mutually exclusive, right? You could have 4 suits and some of them be aces, so they don't all add up to 52 in this. So let's see. how many cards are face cards or aces? How many are face cards or aces? Well, how many face cards do we have? Well, we have 12 face cards. So the way that we can write that actually would say this, that the number of face cards is equal to 12. Now, what's the number of aces? We have exactly 4. So because these are mutually exclusive, I cannot pick a card that is both a face and an ace. So the only way for this to work is we add these together, and the answer is 16. And the way we can write that is that we have 16, the number of ace or face.
Can we just do that?
So this brings us to our counting principle. And it says if two finite sets, A and B, are mutually exclusive, then the number of the union of the two, the U is union, is simply just the number of A plus the number of B. Now, how is that different? That's going to be different down here. And this, of course, is just called the general form, because mutually exclusive here, if it were mutually exclusive, then this n of the intersection is just the null set. So there is nothing. So in subtracting an empty set, you still get the same thing. So this one is, if you know it's mutually exclusive, then just go ahead and add them together. But if you just want to remember one thing, just remember this one down here. So that brings us here, where we add the numbers of one set and the numbers of the other set, and we subtract the intersection to account for the double counting. So here's the example of that. In a standard deck of cards, how many cards are even and red? Okay, and how many are even or red? So we're going to need to know a whole bunch of things. Number one, we need to know how many even there are. We need to know how many red there are. Then we also want to know how many and, right? So even and red. And then here we want the even or red. So let's actually do with the red first, because that's easiest. The red cards are exactly half of them. One way to write it, of course, is simply just to say the 26 red out of 52. So then we simplify. We already know it's 1/2, so you could have started there. That's fine. But I wanted to write it in this first one here just so you know it's out of 52, because that's what's going to help us out in the next one. With the even, 52, we have to count up how many even cards we have.
There's 20.
So, well, how many even cards? We don't have, so we have 2s, 4s, 6, and 10s.
What about 8?
And an 8, thank you. Now, so we've got 5 of those times 4 suits, right? Times 4 suits. So in the end, there are 20. So 20 even. And when we reduce that, we get 5 out of. Now, of course, how can we get to 5 out of 13 quicker? Notice here, 1, 2, 3, 4, 5 per suit. So we just said 5 out of the 13 in the suit. So you could have just jumped to the simplified right there. Okay, well, how many are even and red? How many are even and red? Well, we know that there are 52 cards. And since there are 2 reds that have 5, we say there are going to be 10 total for there. So now we can reduce this, which is half the one we had earlier, which is 5 out of, 5 out of 26. So that actually answers one of the questions, the even and the red, the intersection of the two. So that's going to help us calculate the or. How many are even or red? Well, we're going to use this rule down here. We're going to take the number of even plus the number of red and subtract the ones we counted twice. So we're going to have to subtract that one. So I'm going to keep it all in the 52s because it already has a common denominator there. So the first one here is, we're going to say 20 over 52 plus the 26 over 52, which is the red cards. And then lastly, we're going to get rid of one of the double countings. That's the intersection of those. And as you see here, that becomes 10. So 36 over 52. Divide by 4 to be 9 out of 13. All right, so my apologies, I went to the next level, because obviously we need to know the counting in order to go to the next level. So my mistake, the original was 20 here, the counts are just the 26 and the 10, and in the end here, the count is, there are 36. So my apologies, 36. I jumped the gun. This is actually the answer to the next one, which says that, so this is the count right there, 36. When we answer the question, what's the probability of drawing an even or a red, then the answer is 9 out of 13, because we just do the favorable, which is 36, over the total, which is 52. So the answer is actually 26 students. And let's see how we got that. There's, the book will have a more complicated way to do it. I'll just explain it a faster way. Notice that when the school counts how many students study French, Spanish, or both, all they do is just say, well, how many are enrolled in the classes? And when they add it all up, they get 298 students total. Now, clearly that doesn't mean individual students. It just means how many seats are taken up in those classes. So some students are accounted for twice. So the school reports that 115 are in French, 115 in French, plus the 209 that are in Spanish. So when we add those together, so 324. But of course we have a discrepancy, right? Wait, the school says only 298. So how many are counted twice? Well, if we subtract the 298 here, we get 26. So all we do here is account for the double by finding out what the difference is between the two there. All right, now this brings us directly to probability. And the probability is exactly like we did earlier when I made that mistake. If A and B are any event in the same finite sample space, then the probability of A or B happening, which is, of course, the union of A, B, then we add the probabilities together and we subtract the overlap. We subtract the overlap. Remember, in the case of mutually exclusive are going to be the null set there. So it's just adding the two probabilities together and that's it. So this one we actually already went through part of the way. So let's go ahead and go all the way similar through this one. So what's the probability of choosing a face card? Well, we know that there are a total of 3 face cards per suit. Then we know there are 4 suits. So we do know that there are 12 face cards. So 12 out of 52 is equal to 3 out of 13. So this is the probability of choosing a red card. 3 out of 13. Sorry, face card. For the probability of choosing a red card, we know that half the deck is red. So then that equals just 1/2, or 26 out of 52 of them are red. Probability of choosing an even, we already did that one. So probability of an even, and we counted those off to get 5 out of 13. Again, that was 20 out of 52, and then we brought that one down. So now, what's the probability of... All right, so the probability of even and red. When we count up the even and red, so since there are 10 that are even and red out of 52, so the probability of choosing an even and a red here is going to be 5 out of 26. And here's where we get our probability of even or red. The probability of even or red is we have to take the probability of red, the probability of even, and we subtract the intersection there. Finishing this up, 9 out of 13 is what we get. So the probability is very high. And if we calculated that out, so this is going to be approximately 69% chance, which is in the likely territory of this occurring. So this one does require us to count stuff out. It's not so easy without knowing all the options here. So if a pair of 6-sided dice is thrown, and the dice are fair, what's the probability that the dice shows doubles or some less than 10? Okay. So the first thing is that doubles, we know that there are only 6 out of 36 options there. So that's the probability of doubles. The probability of getting a sum that's less than 10, we have to count them all up. So 1, 1, 1, 2, 1, 3, all the way to 5, 4, which will give me that. So when I count them all up, I get 30 options. There are 30 out of 36. Remember, there are only... Now, that one actually, you could have done it a faster way. What's the faster way? Well, which ones add to 10, 11, and 12? Well, the only ones that add to 10 are 5, 5, 6, 4, and 4, 6. The only ones that add to 11 are 5, 6, and 6, 5. And the only one that adds to 12 is 6, 6. So if you subtract these 6 right here, you would have gotten that faster. Okay? Right. 2 different ways to do it. So here I was thinking about the positive space, just by counting the actual ones. Here I'm talking about the complement, the negative space, where I'm getting rid of what I don't need. Okay, so that gives me the less than 10. Now, of course, when we add those together, we get 100%, right? 36 over 36, and we say, yay, we get 100% of options here. And the answer is no, we actually don't get 100%, because we could have gotten a 5, 6, which is neither a double nor less than 10. So in this case, we are going to find the union, which I just circled those for. So the 6 plus the 30 minus the 4 gives the total number of the or, and then we divide by 36. So in this case, it's a 32 out of 36, which reduces to 8 out of 9. So if we brought that into percentage, the chances are very, very likely. Not 100%, but certainly up there. So this, of course, brings us to what's called complementary events. Complementary events are events that their intersection is 0, the null set. Why? Because they are mutually exclusive. No overlap at all. And their union is the entire sample space. So this is what brings us to complementary events. If A is an event, so for example, the probability of getting red, then the probability of not getting red is just 100% minus that probability, or 1 minus the decimal, whatever it is, or the fraction. So let's take a gander here. So at the Swenson Memorial High School, what is the probability of randomly selecting a student who is not studying both French and Spanish? And of course, let's just clarify this at the Swenson Memorial High School, and we're going to focus on in the French and Spanish classes. So not the entire school. We're going into the French and Spanish classes and randomly selecting somebody. Okay. So the question is, in that sample space of those French and Spanish classes, what's the probability of randomly selecting a student who is not studying both French and Spanish? So we know that the probability of both, studying both, is equal to the 26 over the 298 total students. So since we're choosing the not, all we have to do is say 1 minus 26 over 298. So in the end, we get 272 out of 298. And if we approximate that, 91.2% chance. So both of these are answers. This can be reduced. All right, and the last thing I want you to look at here is go ahead and walk through this one. What is the probability of choosing a non-red card? And what's the probability of choosing a not even or red? So, by the way, watch this. I want to say not even or not red. Maybe that's a better not even or red. So take a gander at those. So in just taking the complements here, not red is 1 minus half. The not even or not red is 1 minus the 9 over 13. So we get 4 out of 13 for that.